Hi, and welcome to this fifth episode of our MiniStealth tutorial series where we're creating a small roguelike stealth game using SpriteKit and GameplayKit. And today we're going to be working on visibility using shadow casting. And it's going to be a big day because this is our first time we're really starting to use the component system in GameplayKit. So we already worked with entities, now we're adding components, and we'll do so by implementing our first component, the visibility component. And this way we integrate components into the game, and that helps us set up sort of a skeleton for and quite a flexible engine where we can add additional functionality quite easily simply by adding additional components as required. And that's just what we'll be doing in future episodes. Visibility is kind of a slightly more complex topic, so there will be quite a bit more code in this episode than in the other ones. And also working with the entity component system in GameplayKit can be a bit daunting at first, so it's a sort of a step up, but don't worry, we'll go through it step by step. So let's first talk about visibility. So exploration is typically a fun part of roguelikes, but basically any type of game. So we want to add a sense of exploration to this game by not showing the map in its entirety at the start, but showing it piece by piece and simply limiting the field of view of the player. And we'll do so by distance, so you won't have unlimited view distance. And we'll also perhaps other obstacles obstruct field of view, so you won't be able to see, for instance, through a corner. And to calculate what you can and cannot see, you use a visibility algorithm, and there are many different types. So some are very simple, some are a lot more complex. Typically they have a trade-off between how accurate they are, how fast they are, how complex they are. And we'll be using the shadow casting technique here because it's a pretty good trade-off. It's not trivial to implement, but it's not overly complex either. And if you want to know more about visibility algorithms, the Rogue Basin has a great write-up of various algorithms, including examples. So we'll be using shadow casting. We won't be writing all that code because it's a lot of code and it's really bad Swift because it's a literal translation. So I'll give a link to a text file where you can find the code itself. What we will do is implement all the code that's needed to get it running within the game. So what we want is visibility to be entity dependent, so each entity can have a different field of view and thus a different set of visible tiles. I assume that once you've seen a tile, then it becomes a known tile. So even though you can't see it, you still know it's there, so you might know the way back. And we'll use a visibility component to store all that information, and we'll do so in a dictionary that maps a location, a coordinate, which we describe as a vector, to a visibility. And visibility is an enum that has three cases. Either you haven't visited or haven't seen a tile yet, so we call it not visited. Either you've seen it in the past but it's not visible right now, then we call it visited. And if you can see it right now, we call it visible, and we'll also store how much light we can see, so how close it's to the entity that holds the visibility component. It's a subclass of the GK component, and we will be needing the visibility, the position of the player, so we'll extend GK component with a computed variable that gives us easy access to the entity itself. Get into that during code a bit more. And each turn we update the list of visible tiles. Now, updating each turn we will do by creating a protocol world updatable. We won't be using the GK component's own update function because we also need the world context. Basically, we need to know, we need to map and everything else that's in it to calculate visibility correctly. And we'll make sure that both visibility component and MS entity component conform to world updatable. And then each turn we will call update in for all entities, and then for each entity we'll call update in for each component that conforms to world updatable. So then we have a chain where we're updating each component for each entity and thus have updated our world. At least that's how we define updating our world. So our implementation sequence, we will first create the world updatable protocol and add protocol conformance to MS entity. Then we'll implement the visibility component. That's probably the largest part of the video. Then we set up the update chain. We go from a game scene to the world to the entity to world updatable components. And then we'll change the show map function to take visibility into account. And while we're doing that, we'll also touch up on vector and cell as as needed. So let's start by creating the world updatable protocol and adding protocol conformance to MS entity. So let's create our new file, a Swift file in our model folder, and we'll call it world updatable. And this will define a protocol, a world updatable, and it will only have one requirement, a function update in world. And that's it. Then we go to MS entity and we add protocol conformance to world updatable. And this means that we need to implement the update in function. We'll add code later, but this is enough to satisfy the protocol. And while we're at it, we'll also add our convenience accessor to GK components, so we can have access to the MS entity that owns the component. So we'll see if we can find an MS entity equals entity. This one is part of every GK component, always knows about the entity that owns it. But it might not be an MS entity, and this is what we're going to try here. We'll try and cast it to an MS entity, and if this fails, we'll send out an error message that we should only use entities in this game. This way we can, in a component, very easily get the owning MS entity from it, and then we know its name, its position, and perhaps other stuff we need in the future. So if this works, we'll send back the MS entity. So this is just a bit of convenience, otherwise you would have to more or less write this code each and every time that you need access. So either an owning entity's position or name or anything else. So this should be enough to add world updatable protocol and add protocol conformance. Now it's time to implement our first component, the visibility component. And we'll create a new group for components. And in this we'll add a new file called, a new Swift file called VisibilityComponent. And this one requires GameplayKit because we want to our visibility component to inherit from GK component, and it also should conform to world updatable. Now, what do we want to know about or what do we want our visibility component to have? Well, it should have a vision range, and it should have our dictionary of tiles that map from location to visibility. And note we haven't defined visibility yet, so we'll do so right now. So we will have an enum called visibility, and it will have three cases. It will have a case not visited, so it's invisible. It will have visited. It's not visible right now, but we know about it. And we have a case visible, and we'll add how much light it's receiving in lit associated value. So this one should now be able to work. We will need an initializer that takes the tile visibility. I'm sorry, this will take a vision range. And we'll call the superclasses init function. Visibility. Okay, cool. We'll add the required initializer, and we also need to add an update function. And we'll add the code that we require there in a bit. So first let's start adding the shadow casting code. So this code I will copy from this text file because as said, it's really not great Swift code. And it's also a lot of code. What's interesting is how we can use it in our game. So what it requires is to refresh each octant. So what we'll do is we'll create a function called update visibility for our map, and we'll go for each octant 0 to 7. Correspond to the cases right here. We'll do refresh octant in the map that was passed in and the octant. And what we also should do is should start with clearing the current visibility. But we haven't defined that one yet, so we'll create a clear visibility function. And all this will do is it'll go through each tile in tile visibility, and it will set the tile visibility for the location to visited. So this way all the tiles that were at least either once visible or once visited will remain visited. And let's see. So we have a clear visibility. Typing is sometimes difficult. And now we can also implement our update function, because we'll just call update visibility in world.map. I'll just add a quick print. Visibility component update. So we can see that it's being called correctly. Now there are a couple of errors in the code we just passed in, and the first one is we have a vector here, but we don't have a distance function yet. So this is something we can add. We'll create a static func distance, and it will take 2 vectors, and it will return a double. So we want to have the distance between these vectors, which is basically the length of a vector that's the difference between these two. So ideally we would create a new vector that's where one vector, the one vector is subtracted for the other one, but we can't do that yet. But what we can do is create a subtraction method, and now we have a vector that we can determine the length of, and this takes Pythagoras theorem. So we'll take the square root of vector.x times vector.x plus vector.y times vector.y. This will be an integer, so we'll cast it to a double, and this should be a distance function. So this one should stop complaining. And the second one is it expects a cell to have a blocks light property, which it doesn't have yet. So we have in cell already an enterable property. We'll add blocks light property because something might not be enterable but still block light or vice versa. So we'll keep those separate. So blocks light will assume that everything blocks light unless specified otherwise. In this case, a floor doesn't block light. So this should now get rid of the error right here. This should also build. All right. And now let's set up the update chain from game scene to world to entity world updatable component. So basically we're setting up the entire update chain, and we'll start at the top at the game scene. So we have our show world here, which we show each turn. After we clear the console, we'll say world.update. But we haven't implemented defined world.update yet, no problem. We'll go to world. I will add a function called update, and all this will do, what this will do is for each entity in entities, we'll call entity.update in ourselves. Then we go to our entity, and we have our update function here, but there's no code yet here. What we'll do is for each component in components, we'll call component.update. And notice that we don't have our update in function here, and that's because component here is a GK component and it doesn't know yet about world updatable. So what we'll do is this, we'll create a temporary variable called world updatable components, and we'll take all the components this entity has and we'll filter out the ones that conform to world updatable. So we'll try and cast a component to world updatable. This returns nil if it fails, and the compact map filters all the nil values out. So we basically get back an array of world updatables. So if we use this one here and now ask component.update, we have our update.world function. And now we should be able to update all the components. We already implemented the visibility component. Now let's make sure that our player actually has a visibility component. So we'll add a component here called visibility component. With vision range, we'll give the vision range of 10. And if we run this, if we haven't made any big mistakes, we should in the output window here see each time the visibility update component update is called. We can't see the result yet because we're not using the visibility data yet, but that's the next step. So let's go back to our visibility component, get rid of this update or this print function statement in the update, and go to the next step, and that's changing the show map function of game scene to take visibility into account. So we'll go into the game scene. We have a code here that shows all cells and all entities. We'll comment that one out, and we more or less have to start over a bit. So first what we will do is we'll try and get a visibility component. So for the player. So we have a world player, and we want to have a component of type visibility component. This is how you get a specific component in GameplayKit. This returns an optional, so we need to unwrap it here if it's available. So now we have a visibility component, and what we can do is for each tile in the visibility component tile visibility, these are all visible tiles, or at least tiles that are either visible or visited. And we'll say a map cell is, we'll see what kind of cell it is, And we'll do it for the tile.key because that's the location. And then we can switch on the tile.value. And if it's not visited, well, then we simply don't do anything. If it's visited, we take this value here. Well, we have our map cell .name, we have a location, and as a color we will use dark gray. And if it's visible, we'll get the visibility value as well. And then we'll do something similar, but this time, names are a bit different here. As the brightest, we'll use the lit value. So this way, the more lit it is, the brighter it will look. And this will give the idea of a player holding a torch and being able to see better what's closer by. And I think what we should now have is just the map showing, so just the walls and the floors, and you can see the light, but once they're out of range or out of sight, then you see them as see the tiles as dark gray. You can see see what the shadow is doing. So this works pretty cool. We don't see the entities yet because we need to do something similar for them. So we'll go for each entity in entities. And what we'll do is we'll have the visibility be, we'll see whether this is a tile we know about in the visibility component. But if it's not, then we assume it's not visible at all. Then we'll do something similar as before. So we'll switch on the visibility and we'll say case not visited, we won't do anything. If it's visited, then we will not show it either because it's not directly visible and we don't know whether it moved. So we won't show entities that are sort of in the fog of war. And finally, if it is visible, then again we will take the lit value, and we will take this one. So we have our entity name, put it on the foreground, and we, as the brightness, we will use the lit value. And we should now see the entities as well if we run. So we see the player, that's cool. We can see the enemy. So this works. So I think this meets our goal for today. For next time, what we will be doing is we'll be adding we'll have our enemies start walking around, start patrolling, start trying to hunt out the player. So we'll use state machines to model that behavior, and we'll implement a very naive pathfinding. So it won't be a very smart enemy who gets stuck between walls very easily and so on. We'll implement better pathfinding using GameplayKit later, but this is a good start to at least get the basic behavior of the enemy working. And again, we'll use a component to implement it. So thanks for watching and have a good day.